Now, question number 2 involves a train traveling up a hill. And the idea here is that the back car of the train, I guess, detaches or breaks free and begins to coast without friction. So it may help if I just draw this right here. Yeah, I'll draw it over on the left. So the rest of the train, so all these cars up here, and you might say there's our engine pulling everything, have gone up the hill. But this car has broken free and begins to coast. Oh gosh, dropped my pen. And begins to coast. Well, the original velocity of all the cars, or you might say the initial velocity, is 3.25 meters per second. 3.25 meters per second. Well, what's going to happen to this car if it was being pulled up the hill 3.25 meters per second, but now it is broken free from the train? Well, it's going to start coasting to a stop, and then we can expect that it will probably start to roll back down the hill because it doesn't have any power. So really, this is a kinematics question. The question is, how long does it take for the last car to come to rest? Now, the initial velocity is 3.25 meters per second. If it's coming to rest, well, we know that means that the final velocity, VF, is 0 meters per second. Now, we're used to problems like this where we say you throw a ball up in the air at, say, 3.25 meters per second. That's your initial velocity. And, of course, in midair, it stops and comes back down. And we can calculate how long it would take to do that because we know the acceleration. And in that case, the acceleration of gravity is what slows the ball down and brings it back down. In this case, the acceleration of gravity still comes into play. But instead of working straight down, we would say A is negative 9.81 meters per second squared. Instead of working straight down, it's going to be working kind of at an angle. That is to bring this car to a stop and then send it back down the hill the other way. So let me redraw this over here on the stop. Here we go. So really, here's our hill, and it's a 3.73 degree incline. That's pretty specific there. 3.73 degrees. And the acceleration of gravity, or we're just going to call it G. Now, this isn't a force. It's actually an acceleration. G is acting straight down. But what we want to know is what we might call G parallel. That acceleration that we know always acts in the y direction downwards. We'll call this G parallel right here. There's also, you could say, there's a perpendicular component to it. We might call that G perpendicular. But what is really slowing the train to a stop is this G parallel right here, because it's acting along the same plane, you might say, along the same surface that the train is moving. So that is going to become our acceleration, or really our deceleration that causes the train to come to a stop. If we can find that, and if we know our initial velocity, and if we know our final velocity, it should be very easy then to use this as our deceleration to find time. Well, what is it? What is our you might say, our parallel G, or our parallel acceleration? Well, let's write down what our G is, and we all know that G is 9.81 meters per second squared. Well, just like we find the parallel weight force and the perpendicular weight force, we can do this with g. So g, which is an acceleration, g parallel, that would be g times the sine of theta. Just like we did before in our other problems. It's the full value, you might say, of the force times, in this case, the sine of theta. So that would be 9.81 sine of, man, that is a very specific angle, 3.7, I'll put this in parentheses here, 3.73. That's a degrees, 3.73 degrees. Okay. 9.81 sine 3.73. I get 0.64 or 0.64. That 0 looks kind of like a 6, doesn't it? 0.64 what? Well, it's an acceleration, so it would be 0.64 meters per second squared. That is going to be that parallel to the rails acceleration of gravity. That's going to be what slows the train to a stop. So we'll say our g parallel equals the acceleration. And in this case, we can look at this and say, okay, it's going to serve to be a as a deceleration, you might say. So we'll put a negative in front of it, but that's just really the value or the absolute value of the acceleration force. Negative 0.64 meters per second squared. Well, we know the initial velocity, right? That's 3.25 meters per second. And of course, the final velocity, it's coming to a stop, is 0 meters per second. We have acceleration, initial velocity, final velocity. We're solving for time. We don't know that, but we soon will, because we know that v final equals v initial plus acceleration times time. That means that solving for time, that would be, do that, equals v final minus v initial over a. So 0 minus 3.25 over our newly found acceleration, or you might say our deceleration, negative 0.64, as in 0.64 meters per second. So negative 3.25 divided by negative 0.64, I'm going to say 5.1. 5.1 seconds. That's the amount of time it takes for that train to come to a stop. Now, of course, we know after that, the train is probably going to start drifting back downhill, but that's how long it takes to go from V initial to V final, as of course, the rest of the train goes up the hill. Now, part B is kind of an extension of this, and it's actually pretty easy. The question is, how far did the last car travel before momentarily coming to rest? Now, again, the key word is momentarily. It comes to rest for a fraction of a second before gravity pulls it even further back down the hill. But how far did it travel before coming to rest? Well, once again, we know the initial velocity is 3.25 meters per second. Our final velocity is 0 meters per second. Our acceleration, or you might say our deceleration, negative 0.64 meters per second squared. And we want to find how far it travels, for how far it traveled. I'm going to say, well, I'm just going to call it delta x. We could call it a number of things. How about delta x parallel, to be more specific? How far did it travel parallel to the rails? That's indicating that it's moving along, still kind of up the hill. Well, we can solve this. We have an equation, v final squared equals v initial squared plus 2a times, and in this case, delta x, that's a bad delta, up to a, not a very good a either, delta x, we'll say parallel to the tracks. Well, if we want to solve for delta x, that would be vf squared minus vi squared over 2a. So 0 minus 3.25 squared divided by 2 times negative 0.64. And that gives us a distance of 8.28 meters. 8.28 meters. So that's how far it goes before it stops. This is how long it takes to drift to a halt, and this is how far it goes. And this is all based on the fact that not just forces, but also accelerations can be broken into perpendicular to the hill and parallel to the hill components. We know how to do that. We can now apply that to other scenarios. There we go. That's question 2 of homework 7.1. I'll see you on the next video for homework problem 3. See you then.